This lecture consists of two parts that deal with two rather different topics. In the first part, we look into an important special case of a derived distribution problem. We start with two independent random variables with known distributions and wish to find the distribution of their sum. We will see that for either the discrete or the continuous case, there is a nice formula that gives us the answer. We will develop this formula, and then we will talk a little bit about a graphical way of carrying out the calculations involved. As we will discuss, this formula also allows us to establish the very important fact that the sum of two independent normal random variables is normal. In the second part, we introduce the covariance of two random variables and the correlation coefficient. These are certain quantities that allow us to quantify the degree to which two dependent random variables are related. For example, a high value of the correlation coefficient will indicate a strong relation between these random variables. We will see the basic mathematical properties of these quantities and provide some interpretation. Later on in this class, we will see that they play an important role in the problem of estimating one random variable given the value of another.
The subject of this segment is the calculation of the PMF of the sum of two independent discrete random variables. This is the simplest example of a function of two random variables, a function of the form g of x and y, where the function g happens to be just the sum of the two arguments. This is a very important example because there are many situations where random variables get added to each other. We work with discrete random variables as a warm-up, and later we will consider the case of continuous random variables. So suppose that we know the PMFs of x and y, and that we want to compute the probability that the sum is equal to 3. It always helps to have a picture. The sum of x and y will be equal to 3. This is an event that can happen in many ways. For example, x could be 3 and y could be 0, or x could be 1 and y be equal to 2. The probability of the event of interest, that the sum is equal to 3, is going to be the sum of the probabilities of all the different ways that this event can happen. So it is going to be a sum of various terms, and the typical term will be the probability, let's say, of this outcome, which is that x is equal to 0 and y is equal to 3. Another typical term in the sum will be the probability of this outcome here, the probability that x is equal to 1, y is equal to 2, and so on. Now, here comes an important step. Because we have assumed that x and y are independent, the probability of these two events happening is the product of the probabilities of each one of these events. So it is the product of the probability that x is equal to 0, where now I'm using PMF notation, times the probability that y is equal to 3. Similarly, the next term is the probability that x is equal to 1 times the probability that y is equal to 2. Again, we can do this because we are assuming that our two random variables are independent of each other. Now let us generalize. In the general case, the probability that the sum takes on a particular value little z can be calculated as follows. We look at all the different ways that the sum of little z can be obtained. One way is that the random variable x takes on a specific value little x, and at the same time the random variable y takes the value that's needed so that the sum of the two is equal to little z. For a given value of x, of little x, we have a particular way that the sum is equal to z. And this particular way has a certain probability. But little x could be anything, and different choices of little x give us different ways that the event of interest can happen, so we add those probabilities over all possible x's. And then we proceed as follows. We invoke independence of x and y to write this probability as a product of two probabilities, and then we use PMF notation instead of probability notation to obtain this expression here. This formula is called the convolution formula. It is the convolution of two PMFs. What convolution means is that somebody gives us the PMF of one random variable, gives us also the PMF of another random variable, and when we say we're given the PMF, it means we're given the values of the PMFs for all possible choices of little x and little y, the arguments of the two PMFs. Then the convolution formula does a certain calculation and spits out now a new PMF, which is the PMF of the random variable z. Let us now take a closer look of what it takes to carry out the calculations involved in this convolution formula. Let us proceed by a simple example that will illustrate the methodology. We're given two PMFs of two random variables, and assuming that they're independent, the PMF of their sum is determined by this formula here, and we want to see what those terms in this summation would be. Suppose that we're interested in the probability that the sum is equal to 3. Now the sum is going to be equal to 3. This can happen in several ways. We could have x equal to 1 and y equal to 2. This combination is one way that the sum of 3 can be obtained, and that combination has a probability of 1/3 times 3/6, and that would be one of the terms in this summation. Another way that the sum of 3 can be obtained is by having x equal to 4 and y equal to -1, and by multiplying this probability 2/3 with 2/6, we obtain another contribution to this summation. However, keeping track of these correspondences here can become a little complicated if we have richer PMFs, so an alternative way of arranging the calculation is the following. Let us take the PMF of y, flip it along this vertical axis. So these two terms will go to the left side and this term will go to the right hand side, and then draw it underneath the PMF of x. This is what we obtain. Then let us take this drawing here and shift it to the right by 3. So the entry of -2 goes to 1, -1 goes to 2, and 1 goes to 4. So what have we accomplished by these two transformations? Well, the term that had probability 3/6 and which were to be multiplied with the probability 1/3 on that side, now this 3/6 sits here. So we have this correspondence and we need to multiply 1/3 by 3/6. Similarly, the multiplication of 2/3 with 2/6 corresponds to the multiplication of this probability here times the probability of this term here. So when the diagrams are arranged this way, then we have a simpler job to do. We look at corresponding terms, those that sit on top of each other, multiply them, do that for all possible choices, and then add those products together. And this is what we do if we're shifting by 3. Now, if we wanted to find the probability that z equal to 4, we would be doing the same thing, except that this diagram would need to be shifted by 1 more unit to the right, so that we have a total shift of 4. So we just repeat this procedure for all possible values of z, which corresponds to taking this diagram here and shifting it progressively by different amounts. This turns out to be a fairly simple and systematic way of arranging the calculations, at least if you're doing them by hand. Of course, an alternative is to carry out the calculations on a computer. This is a pretty simple formula that is not hard to implement on a computer. We now develop a methodology for finding the PDF of the sum of two independent random variables when these random variables are continuous with known PDFs. So in that case, z will also be continuous and so we'll have a PDF. The development is quite analogous to the one for the discrete case, and in the discrete case we obtained this convolution formula. This convolution formula corresponds to a summation over all ways that a certain sum can be realized. In this picture, these are all the ways that a sum of 3 can be realized. In the continuous case, the different ways that a constant sum can be realized corresponds to a line. So this is a line in which x plus y is equal to a constant. And we need to somehow add over all the possible ways that the sum can be obtained, add over all the points on this line. Now, when we're summing over all the points of the line, we really need to employ an integral. And this leads to the following guess for the formula. Instead of having a summation, we will have an integral. And the integral is over all the x, y pairs whose sum is a constant number, little z. So we have here the familiar recipe that sums are replaced by integrals and PMFs are replaced by PDFs. So this formula is entirely plausible and it is called the continuous convolution formula. What we want to do next is to actually justify this formula more rigorously. We will use the following trick. We will first condition on the random variable x taking on a specific value. If we do this conditioning, then the random variable z becomes little x plus y. And to make the argument more transparent, we're going to look first at a special case where little x is, let's say, the number 3, in which case our random variable z is equal to y plus 3. Let us now calculate the conditional PDF of z in a universe in which we are told that the random variable x takes on the value of 3. Now, given that x takes on the value of 3, the random variable z is the same as the random variable y plus 3. And now we have the conditional PDF of y plus 3 given x. However, we have assumed that x and y are independent. So the conditional PDF is going to be the same as the unconditional PDF of y plus 3. And we obtain this expression. Now, what is this? We know the PDF of y, but now we want the PDF of y plus 3. Which is a simple version of a linear function of a single random variable y. For a linear function of this form, we have already derived a formula in the notation we have used in the past. If we have a random variable x and we add a constant to it, the PDF of the new random variable is the PDF of x, but shifted by an amount equal to b to the right, and that's what this shifting corresponds to mathematically. Now let us apply this formula to the case that we have here. We need to keep track of the different symbols. So capital Y corresponds to x, b corresponds to 3, little x corresponds to z, and by using these correspondences, what we obtain is f sub y of this argument, which is z in our case, minus b, which is 3 in our case. And this is the final form for the conditional density of z given that x takes a specific value. It's nothing more than the density of y, but shifted by 3 units to the right. Let us now generalize this. Instead of using x equal to 3, let us use a general number. And this gives us the more general formula that the conditional PDF of z, given that x takes on a specific value, is equal to, just use little x here instead of 3, it takes this form. So we do have now in our hands a formula for the conditional density of z given x. Since we have the conditional and we also know the PDF of x, we can use the multiplication rule to find the joint PDF of x and z. By the multiplication rule, it is the marginal PDF of x times the conditional PDF of z given x, which in our case takes this particular form. And now that we have the joint PDF in our hands, we can use another familiar formula that takes us from the joint to the marginal. If we take the joint PDF and integrate with respect to one argument, we obtain the marginal PDF of the other random variable. Using this specific form that we have for the joint PDF in this formula, we have finally obtained this expression. This is the integral of the joint PDF of x with z integrated over all x's, and this proves this convolution formula. In terms of the mechanics of carrying out the calculation of the convolution, the mechanics are exactly the same as in the discrete case. If you want to solve a problem graphically, what you will do is to take the PDF of y, flip it horizontally, and then shift it by an amount of little z, cross-multiply terms, and integrate them out. In this brief segment, we discuss an important application of the convolution formula. Suppose that x is a normal random variable with a given mean and variance, so that the PDF of x takes this form. And similarly, y is normal with a given mean and variance, so its PDF takes this form. We assume that x and y are independent, and we're interested in the sum of the two random variables, x and y, and we wish to derive the PDF of z. Of course, the PDF of z is given by the convolution formula. And now we plug in here the form for the density of x, and here we plug the form of the density of y, except that instead of the argument y, we need to put in the argument z minus x. So we obtain this form where here we have a z minus x instead of y. Now this is an integral that looks pretty complicated, but it is not too hard to do. One just needs to be patient, rearrange terms, collect terms, and the details of the calculations are not as interesting, so we will skip them for now, and I will just tell you that the final answer takes this form. What is this form? Well, it's exponential of minus z minus something squared divided by a constant, and we recognize that this is the form of a normal random variable. It's a normal random variable whose mean is given by this term here. It's mu x plus mu y. And the variance of that normal random variable is that constant that appears next to the factor of 2 in the denominator. So the sum of these two normal random variables, these two independent normal random variables, is also normal. The fact that this is the mean and this is the variance of the sum, of course, is not a surprise. What is important in this result that we have here is that the sum is actually normal. Now we carried out this argument for the case of the sum of two normal random variables. But suppose that we had the sum of three independent normal random variables. What can we say about it? By the result that we just discussed, this sum is normal. This is assumed to be normal. We assume that x, y, and w are independent. Therefore, this sum is independent from w, so we're dealing with the sum of two independent normal random variables again, so this sum here is going to be normal as well. And we continue this argument by induction and conclude that more generally the sum of any finite number of independent normal random variables is normal. This is a very important but also useful fact. It means that when we start working with normal random variables, very often we stay within the realm of normal random variables. We can form linear functions of them, take linear combinations of them, and still remain in the world of normal random variables. In this segment, we start a new topic. We will talk about the covariance of two random variables, which gives us useful information about the dependencies between these two random variables. Let us motivate the concept by looking first at a special case. Suppose that x and y have zero means and that they are discrete random variables. If x and y are independent, then the expectation of the product is the product of the expectations. And since we have assumed zero means, this is going to be equal to 0. But suppose instead that the joint PMF of the x and y is of the following kind. Each point in this diagram is equally likely, so we have here a discrete uniform distribution on the discrete set, which consists of the points shown in this diagram. What we have in this particular example is that at most outcomes, positive values of x tend to go together with positive values of y, and negative values of x tend to go together with negative values of y. So most of the time we have outcomes in this quadrant in which x times y is positive, or in this quadrant where x times y is again positive, but some of the time we fall in this quadrant where x times y is negative, or in this quadrant where x times y is negative. Since we have many more points here and here, on the average, the value of x times y is going to be positive. On the other hand, if the diagram takes this form, then most of the time the pair xy lies in this quadrant or in that quadrant where the product of x times y is negative, so the random variables x and y typically have opposite signs, and on the average the expected value of x times y is going to be negative. So here we have a positive expectation, here we have a negative expectation of x times y. This quantity, the expected value of x times y, tells us whether x and y tend to move in the same or in opposite directions. And this quantity is what we call the covariance in the zero mean case. Let us now generalize. The random variables do not have to be discrete. This quantity is well defined for any kind of random variables. And if we have non-zero means, the covariance is defined by this expression. What we have here is that we look at the deviation of x from its mean value and the deviation of y from its mean value, and we're asking whether these two deviations tend to have the same sign or not, whether they move in the same direction or not. If the covariance is positive, what it tells us is that whenever this quantity is positive, so that x is above its mean, then typically or usually the deviation of y from its mean will also tend to be positive. To summarize, the covariance in general tells us whether two random variables tend to move together, both being high or both being low, in some average or typical sense. Now, if the two random variables are independent, we already saw that in the zero mean case, this quantity, the covariance, is going to be zero. How about the case where we have non-zero means? Well, if we have independence, then we have the expected value of the product of two random variables. X and y are independent, so x minus the expected value, which is a constant, is going to be independent from y minus its expected value. And so the covariance is going to be the product of two expectations. But the expected value of x minus this constant is 0, and the same is true for this term as well. So the covariance in this case is going to be equal to 0. So in the independent case, we have 0 covariances. On the other hand, the converse is not true. There are examples in which we have dependence but 0 covariance. Here's one example. In this example, there are 4 possible outcomes. At any particular outcome, either x or y is going to be 0. So in this example, the random variable x times y is identically equal to 0. The mean of x is also 0, the mean of y is also 0 by symmetry, so the covariance is the expected value of this quantity, and so the covariance in this example is equal to 0. On the other hand, the two random variables x and y are dependent. If I tell you that x is equal to 1, then you know that this outcome has occurred. And in that case, you are certain that y is equal to 0. So knowing the value of x tells you a lot about the value of y, and therefore we have dependence between these two random variables. In this segment, we discuss a few algebraic properties of the covariance. There is nothing deep here, only some observations that can be useful if we want to carry out covariance calculations. We start by looking at this quantity, the covariance of a random variable with itself. So it's a special case of this definition, but where y is the same as x, and therefore this second term here is the same as the first term. And so what we're left with is the expected value of the square deviation of the random variable from its mean. And we recognize that this is the same as the variance of x. So we conclude that the covariance of a random variable with itself is the same as the variance. Now for the variance, we had an alternative formula, which was often convenient in simplifying variance calculations. Is there a similar formula for the case of the covariance? Let us start from the definition and use linearity. We have a product here of two terms, and we expand that product to obtain four different terms. The expected value of the sum of these four terms is going to be the sum of their expectations. So let us go through the steps involved. We have the expected value of the product of this term with that term, gives us expected value of x times y. Then we take the expected value of the product of this term with that term. And because we have a minus sign, we put it out here. And we have the expected value of x times the expected value of y inside the expectation. The next term is going to be the product of this expected value with y. And that gives us minus the expected value of x times y. And finally, the last term comes by multiplying this quantity with that quantity. And this is what we have by applying linearity to the definition of the covariance. Now, remember that the expected value of a random variable is a number, it's a constant, and constants can be pulled outside expectations. So if we do that, what we obtain is the following. We pull this constant outside the expectation and we're left with the expected value of x times the expected value of y. Similarly, for the next term, by pulling a constant outside the expectation, we obtain this expression. And finally, for the last term, we have the expected value of a constant, and this is the same as the constant itself. We recognize here that the same term gets repeated 3 times, and because here we have a minus sign, we can cancel this term with that term. And what we're left with is just the difference of these two terms, and this is an alternative form for the covariance of two random variables. And this form is often easier to work with to calculate covariances compared with the original definition. Let us now continue with some additional algebraic properties. Suppose that we know the covariance of x with y, and we are interested in the covariance of this linear function of x with y. What is the covariance going to be? To simplify the calculations, let us just assume zero means, although the final conclusion will be the same as in the case of non-zero means. So in the case of zero means, the covariance of two random variables is just the same as the expected value of the product of the two random variables. And using linearity, this is the expected value times a of x times y plus b times the expected value of y. Now we assumed zero means, so this term goes away, and what we're left with is a times the covariance of x with y. So we see that multiplying x by a increases the covariance by a factor of a, but adding a constant has no effect. The reason that it has no effect is that if we take a random variable and add a constant to it, the same constant gets added to its mean, and so this difference is not affected. As our final calculation, let us look at the covariance of a random variable with the sum of two other random variables. Again, we assume zero means, and so the calculation is as follows. The covariance is the product of the two random variables involved, and then we use linearity of expectations to write this as the expected value of x times y plus the expected value of x times z, and we recognize that this is the same as the covariance of x with y plus the covariance of x with z. So in this respect, covariances behave linearly. They behave linearly with respect to one of the arguments involved. One situation where covariances show up is when we try to calculate the variance of a sum of random variables. So let us look at the variance of the sum of two random variables x1 and x2. If the two random variables are independent, then we know that the variance of the sum is the sum of the variances. But let us now look at what happens in the case where we may have dependence. By definition, the variance is the expected value of the difference of the random variable we're interested in from its expected value squared. And now we rearrange terms here and write what is inside the expectation as follows. We put together x1 with the term minus the expected value of x1, and then x2 together with negative the expected value of x2. So now we have the square of the sum of two terms. We expand the quadratic to obtain expected value of the square of the first term plus the square of the second term plus 2 times a cross term. And what do we have here? The expected value of the first term is just the variance of x1. The expected value of this second term is just the variance of x2. And finally, the cross term, the expected value of it, we recognize that it is the same as the covariance of x1 with x2. And we also have this factor of 2 up here. So this is the general form for the variance of the sum of two random variables. In the case of independence, the covariance is 0, and we just have the sum of the two variances. But when the random variables are dependent, it is possible that the covariance will be non-zero, and we have one additional term. Let us now generalize this calculation. Here is for reference and comparison the formula for the case where we add two random variables, but now let us look at the variance of the sum of many of them. To keep the calculation simple, we're going to assume that the means are 0, but the final conclusion will also be valid for the case of non-zero means. Since we have assumed 0 means, the variance is the same as the expected value of the square of the random variable involved, which is this one. And now we expand this quadratic to obtain the expected value of, we will have a bunch of terms of this kind, where I ranges from 1 up to n, and then we will have a bunch of cross terms of the form xi, xj. And we obtain one cross term for each choice of I from 1 to n, and for each choice of j from 1 to n, as long as I is different from j. So overall here, this sum will have n squared minus n terms. Now, we use linearity to move the expectation inside the summation, and so from here we obtain the sum of the expected value of xi squared, which is the same as the variance of xi, since we assumed zero means. And similarly here we're going to get this double sum over i's that are different from j of the expected value of xi xj, and in the case of zero means again, this is the same as the covariance of xi with xj. And so we have obtained this general formula that gives us the variance of a sum of random variables. If the random variables have zero covariances, then the variance of the sum is the sum of the variances. And this happens in particular when the random variables are independent. For the general case where we may have dependencies and non-zero covariances, then the variance of the sum involves also all the possible covariances between the different random variables. And let me finally add that this formula is also valid for the general case where we do not assume that the means are zero. And the derivation is very similar, except that there's a few more symbols that are floating around. The covariance between two random variables tells us something about the strength of the dependence between them. But it is not so easy to interpret qualitatively. For example, if I tell you that the covariance of x and y is equal to 5, this does not tell you very much about whether x and y are closely related or not. Another difficulty is that if x and y are in units, let's say, of meters, then the covariance will have units of meters squared, and this is hard to interpret. A much more informative quantity is the so-called correlation coefficient, which is a dimensionless version of the covariance. It is defined by this formula here. We just take the covariance and divide it by the product of the standard deviations of the two random variables. Now, if x has units of meters, then the standard deviation also has units of meters, and so this ratio will be dimensionless, and it is not affected by the units that we're using. The same is true for this ratio here, and this is why the correlation coefficient does not have any units of its own. One remark: if we're dealing with a random variable whose standard deviation is equal to 0, so its variance is also equal to 0, then we have a random variable which is identically equal to a constant. Well, for such cases of the general random variables, then the correlation coefficient is not defined because it would have involved a division by 0. A very important property of the correlation coefficient is the following. It turns out that the correlation coefficient is always between -1 and 1. And this allows us to judge whether a certain correlation coefficient is big or not, because we now have an absolute scale. And so it does provide a measure of the degree to which two random variables are associated. To interpret the correlation coefficient, let us now look at some extreme cases. Suppose that x and y are independent. In that case, we know that the covariance is going to be equal to 0, and therefore the correlation coefficient is also going to be equal to 0. And in that case, we say that the two random variables are uncorrelated. However, the converse statement is not true. We have seen already an example in which we have 0 covariance and therefore 0 correlation, but yet the two random variables were dependent. Let us now look at the other extreme, where the two random variables are as dependent as they can be. So let's look at the correlation coefficient of one random variable with itself. What is it going to be? Well, the covariance of a random variable with itself is just the variance of that random variable. Now sigma x is going to be the same as sigma y because we're taking y to be the same as x. So we're dividing by sigma x squared, but the square of the standard deviation is the variance, so we obtain a value of 1. So a correlation coefficient of 1 shows up in such a case of an extreme dependence. If instead we had taken the correlation coefficient of x with the negative of x, in that case we would have obtained a correlation coefficient of -1. A somewhat more general situation than the one we considered here is the following. If we have two random variables that have a linear relation, that is, if I know y, I can figure out the value of x with absolute certainty, and I can figure it out by using a linear formula. In this case, it turns out that the correlation coefficient is either +1 or -1. And the converse is true. If the correlation coefficient has absolute value of 1, then the two random variables obey a deterministic linear relation between them. So to conclude, an extreme value for the correlation coefficient of plus or -1 is equivalent to having a deterministic relation between the two random variables involved. A final remark about the algebraic properties of the correlation coefficient. What can we say about the correlation coefficient of a linear function of a random variable with another? Well, we already know something about what happens to the covariance when we form a linear function, and the covariance of ax plus b with y is related this way to the covariance of x with y. Now let us use this property and calculate the correlation coefficient between ax plus b and y. In the numerator, we have the covariance of ax plus b with y, which is equal to a times the covariance of x with y. At the denominator, we have the standard deviation of this random variable. Now, the standard deviation of this random variable is equal to a times the standard deviation of x, if a is positive. If a is negative, then we need to put the minus sign, but in either case, we will have here the absolute value of a times the standard deviation of x, and then we divide by the standard deviation of the second random variable, which is y. And so what we obtain here is this ratio, which is the correlation coefficient of x with y, times this quantity, which is the sine of a. So we have the sine of a times the correlation coefficient of x with y. So in particular, the magnitude of the correlation coefficient is not going to change when we replace x by ax plus b. And this essentially means that if we change the units of the random variable x, for example, suppose that x was degrees Celsius and ax plus b is degrees Fahrenheit, going from one set of units, Celsius degrees, to another set of units, degrees in Fahrenheit, is not going to change the correlation coefficient of the temperature with some other random variable. So this is a nice property of the correlation coefficient, again, which reflects the fact that it's dimensionless. It doesn't have any units of its own, and it doesn't depend on what kinds of units we use for each one of the random variables. In this segment, we justify some of the properties of the correlation coefficient that we claimed a little earlier. The most important property is that the correlation coefficient lies between -1 and +1. We will prove this property for the special case where we have random variables with zero means and unit variances, so standard deviations are also 1, so most of the terms here disappear, and the correlation coefficient is simply the expected value of x times y. We will show that in this special case, the expected value of x times y lies between -1 and 1. But the proof of this fact remains valid with a little bit of more algebra along similar lines for the general case. What we will do is we will consider this quantity here and expand this quadratic and write it as expected value of x squared Then there's the cross term, which is minus 2 rho, the expected value of x times y, plus rho squared, expected value of y squared. Now, since we assume that the random variables have zero mean, this is the same as the variance, and we assume that the variance is 1, so this term here is equal to 1. Now, the expected value of x times y is the same as the correlation coefficient in this case, so we have minus 2 rho squared, and from here we have rho squared, and by the previous argument, again this quantity, according to our assumptions, is equal to 1, so we're left with this expression, which is 1 minus rho squared. Now notice that this is the expectation of a non-negative random variable, so this quantity here must be non-negative. Therefore, 1 minus rho squared is non-negative, which means that rho squared is less than or equal to 1, and that's the same as requiring that rho lie between minus 1 and plus 1. And so we have established this important property, at least for the special case of zero means and unit variances, but as I mentioned, it remains valid more generally. Now let us look at an extreme case when the absolute value of rho is equal to 1. What happens in this case? In that case, this term is 0, and this implies that the expected value of the square of this random variable is equal to 0. Now here we have a non-negative random variable, and its expected value is 0, which means that when we calculate the expected value of this, there will be no positive contributions, and so the only contributions must be equal to 0. This means that x minus rho y has to be equal to 0 with probability 1. So x is going to be equal to rho times y, and this will happen with essential certainty. Now also, because the absolute value of rho is equal to 1, this means that we have either x equal to y or x equal to minus y in case rho is equal to minus 1. So we see that if the correlation coefficient has an absolute value of 1, then x and y are related to each other according to a simple linear relation. And it's an extreme form of dependence between the two random variables. The mathematics of the correlation coefficient are important, but it is perhaps more important to be able to interpret it correctly. A correlation coefficient of, let's say, 0.5 tells us that something interesting is going on as far as the relation of x and y is concerned. But what exactly? It tells us that the two random variables are associated in some sense, but this is often misinterpreted to mean that there is a causal relation between the two. But this is wrong. A large correlation coefficient in general does not indicate that there is a causal relation between the random variables. As an example, suppose that x somehow quantifies the mathematical aptitude of a person and y somehow quantifies the musical ability of a person. In general, it has been found that mathematical aptitude and musical ability are correlated. People who score high on one will score high on the other as well. Is there a causal relation? If you study math a lot and you become very good at math, does it mean that you will become a better musician? Not necessarily. Or if you practice the violin day in and day out, does this mean that you will score better in the math exam? Again, not necessarily. Perhaps what is going on is that there is a certain feature of the human brain, and when that feature is well developed, then that feature helps both in math and in musical ability. And this is a typical situation of how a correlation coefficient may arise. That is, often a correlation coefficient that's significant reflects that there is an underlying common but perhaps hidden factor that affects both of the random variables x and y. Let us go through a simple numerical example that models a situation of this kind. Suppose that z, v, and w are independent random variables and that we have two more random variables defined by these relations. Notice that there's no direct influence from x to y or from y to x, but on the other hand there is a common underlying factor, this random variable z, that affects both x and y. Because of this, we expect that x and y will somehow have some kind of relation or association between them, and we would like to measure the strength of that association. The way to measure it will be in terms of the correlation coefficient, which we will now proceed to compute. To have a concrete example in our hands, and in order to also keep things simple, let us assume that the basic underlying random variables z, v, and w all have zero means and unit variances. And now let us take the definition of the correlation coefficient and start calculating. Let us look at the variance of x. Because x is the sum of two independent random variables, its variance is going to be the sum of those variances. And we have assumed that each one of those variances is equal to 1, so the variance of x is equal to 2. And that implies that the standard deviation of x is equal to the square root of 2. By a similar argument, the standard deviation of y is also equal to the square root of 2. Now let us look at the covariance between x and y. Because x and y have zero means, the covariance is just the expected value of the product of the two random variables, and using the definition of what these two random variables are, it's this particular product here. We expand the product into a sum of 4 terms and take the expected value of each one of the 4 terms. Which leaves us with this particular expression here. Now, z has zero mean and unit variance, therefore the expected value of z squared is equal to 1. How about the next term? V and z are independent, so the expected value of the product is the product of the expected values, but the expected values are 0, so this term is 0. And with a similar argument, the other terms are 0 as well. So the covariance is equal to 1. And from this we can conclude our calculation and write that the correlation coefficient between x and y is equal to 1 divided by the square root of 2 times square root of 2, which is 1/2. This example also serves to give you a rough idea of what it may mean to have a correlation coefficient of 1/2. It means that the two random variables have some common elements and they also have some idiosyncratic elements, and these two elements are roughly equal in weight. If v and w were completely absent, the correlation coefficient would have been 1. If, on the other hand, v and w had a huge variance, so as to completely hide the effect of z, then the value of the correlation coefficient would have been much smaller, perhaps closer to 0. And in the extreme case, of course, where z is completely absent, then x and y are independent and we get a correlation coefficient of 0. In this segment, we make a connection between the correlation coefficient and some fairly realistic real-world situations. The bottom line will be that the presence or absence of correlations can make a huge difference. Suppose that you run an investment company that invests in real estate and you have 100 million of capital that you want to invest. Now you have learned or believe that it helps to diversify, to not put all of your eggs in the same basket, and for that reason you're going to invest some of your money into different states. You will be investing in 10 different states, and in each state you will invest 10 million, so that your total investment is spread between those 10 states. For each state, you have a model that tells you that the return on your investment, that is your profit, it's of course random, but you expect it to be 1 million on the average, that is in terms of the expected value, but there's also a fair amount of randomness, and so the standard deviation is 1.3. Now, if you look at one state in isolation, it would be a pretty risky investment because the standard deviation is comparable to the mean. It's not an unlikely event to have a return that's one standard deviation below the mean, and if that happens, your return is going to be negative and you're losing money. But then you argue that you're investing in 10 different states. Yes, you might lose money in some of them, but overall, you would expect to have a pretty high confidence that you will end up having a positive return. Is this correct or not? Let us do some calculations. We will look at the variance of your total return. The variance of a sum of random variables is given by the formula that we have developed. It's the sum of the variances, but then you also have a bunch of covariance terms that have to do with the relation of the different random variables. Now you make the assumption that the different states are different markets, one doesn't affect the other, so that the xi's are uncorrelated. In that case, in this variance formula, the covariance terms are all zero and they disappear, and you're left with the sum of 10 variance terms. Now, each one of these variances is equal to the square of the standard deviation, and we have a variance of 16.9. You then take the square root to find the standard deviation, and the square root of this number is 4.1. Now, your expected return is equal to 10, which is 2.5 standard deviations. You will only lose money if the outcome is 2.5 standard deviations below the mean. And that's a fairly unlikely outcome, and so in this situation you feel very confident that you will have a positive profit. Suppose, however, that your assumption is wrong and that actually the different xi's are correlated with each other. And suppose that the correlation is pretty high, 0.9. Essentially, this means that the real estate market in one state is strongly related to the behavior of the market in another state. And that could be perhaps because the markets in different states are affected by some more global phenomenon that operates on a national level. So in this case, the covariance of xi with xj is going to be the correlation coefficient times the standard deviation of xi times the standard deviation of xj, which is 0.9 times 1.3 times 1.3, and so the covariance turns out to be 1.52. And in that case, the variance of the sum using this formula here is going to be equal to 10 times the variance that you have in each state, which is 1.3 squared, plus you have a bunch of terms here. How many terms? There's 90 of them. And each one of these terms is equal to 1.52. And the variance turns out to be 154. Now you take the square root of that and you find a standard deviation of 12.4. Now your expected profit is 10, but the standard deviation is 12.4. And if you happen to be one standard deviation below the expectation, which is something that has a sizable probability of occurring, then your profit is going to be negative. So, in the uncorrelated case, you're pretty certain that you will have a positive profit, but if the correlations actually turn out to be significant, then you're facing a very risky situation. To some extent, this is similar to what happened during the great financial crisis. That is, many investment companies thought that they were secure by diversifying and by investing in different housing markets in different states, but then when the economy moved as a whole, it turned out that there were high correlations between the different states, and so the unthinkable, that is, large losses, actually did occur.